Hi everybody. Today we'll be discussing what is OPL. At a very high level, the Oasis Privacy Layer is a way of connecting Sapphire with other blockchains. This lets you take advantage of properties of each chain for what they do best. For Sapphire, this is the unique combination of being EVM compatible, with contracts that have private state, and access to precompiles which make some things very cheap to do. For other chains, the advantages vary, but let's just assume that that's where your users and their assets are. So the primary method of establishing trust between the two chains is via a message passing bridge. This allows messages to be passed back and forth between the contracts on either chain and assures that when your contracts are invoked, it can trust the content is authentic. A great place to start is the documentation. It provides an overview of how to implement and deploy contracts using OPL. Go to docs.oasis.io and click on the Oasis Privacy Layer button. The OPL documentation also includes a full tutorial on a DAO voting dApp, which demonstrates how to adapt an application to be split across chains using the privacy-preserving features of Sapphire for collecting and tallying votes, with the main interface for the dApp on a transparent chain. Source code can be found on the Oasis Protocol Playground GitHub repository. An important distinction to make is that with OPL, contracts are paired one-to-one with each other, with one contract on the home network and the other contract on Sapphire. When privacy or confidentiality of data submitted by users is necessary, they must interact directly with Sapphire using the wrapped Web3 provider, which provides end-to-end encryption between the user and the smart contract. Where privacy isn't necessary and arguments can be public, users can interact directly with the contract on the home network. The two contracts can then use the message passing bridge to notify each other of actions. Behind the scenes, the message passing bridge is powered by the Seller State Guardian network and an executor. The State Guardian network observes all the supported blockchains and uses a multi-sig authority to sign messages. A small fee is paid when submitting a message for relaying, which covers the cost of running the State Guardians. The executor then monitors the State Guardians, and after a short delay to ensure the block has been confirmed, it will submit a proof on-chain to the message bus, which will then invoke the corresponding message to the target contract. On the Sapphire testnet, the Oasis Protocol Foundation operates an executor which will relay messages for you, but when it comes to deploying your dApp on mainnet or supporting other testnets, you'll need to use the link in the OPL documentation to request that an executor is run for you, or to run your own executor node and pay for gas on behalf of your users. To start using OPL, you will need to add the Sapphire contracts package to your project using pnpm or npm or yarn, whichever you prefer. Then, adapt your contract using the helpers from opl.sol. The most commonly used helpers are Enclave, which your Sapphire contracts extends, Host, which your contract on the home network extends, and the autoswitch function, which fills in the correct message bus address. So let's start by creating a contract on the Sapphire side. Now, remember, we need to import opl.sol to gain access to the Enclave and autoswitch functions. So Sapphire contract is Enclave. So let's import Enclave from here. And in the constructor, we provide the address of the chain, the contract on the other chain, and also the name of the chain which the other contract lives on. and we call the enclave constructor, and use AutoSwitch to provide the message bus address. And in our Sapphire contract, we're going to want to register an endpoint. So let's create a function here called my function, which takes bytes for the call data, which is an arbitrary array that can be decoded to whatever your parameters need to be. So this is an internal function because it must be invoked via the message bus, and you can't call it publicly. And we're going to return a result. So we also have to import the result here. And let's return success. Now that we have our function that the other contract can call via the message bus, we need to register it. So register endpoint and my function is a function. So I'm providing the my function string, which is the name the other contract will use to call this, and then a pointer to my internal function. Of course, you can use whatever function names you want, but the string, the name, is must be called from the other contract. And now we want to decode the arguments. So if we say go to uint256 and a bool, we use the ABI decoder from the args parameter, and we use uint256 and bool as the parameter types. And of course, this will throw an error if the ABI coding isn't correct. And then we can create the contract on the home side, which is sometimes called the host. Home contract.song, and I can copy the start from here, and then from opl.song, I'm going to need the host function. So let's call host, the host class rather, and result as well. Contract, home contract, and host. Let's create the constructor, other end, and we call the constructor for the host class. Now, because it's the host, you don't have to do any auto switching because the host always lives on its own chain, so you can automatically look up the message bus address for that chain. And it's only on the Sapphire contract where you need to tell it which chain the other contract lives on. So there's nothing we need to do in the constructor apart from initialize the inherited class host. But if we want to call the my function that we defined previously, we can use the post message function, which is a part of the host class. So if we say function trigger message, and we gave it a uint256 and a bool, that's an external function. Let's make it payable too, so that people who call this function can call pay the state guardian network fee on behalf of the contract, and we call post message. So it was my function from here, post message with ABR.encode A and B. And if you wanted to create an infinite loop, for example, you could also define a function between register and endpoint in the home contract. Let's call this my other function. And then let's copy in something here, which is my other function. And then from that, you can call the function again. And then in the Sapphire contract, you post a message to my other function with the arguments, and the contract will go back and forth forever until the executor has run out of money to pay for gas. One major advantage of confidential EVM with contracts that can have private state is that by using the built-in VRF, which is the random entropy source, they can generate Ethereum-compatible wallets. In comparison to other blockchains, these operations are very cheap because they use precompiles which are native to Sapphire and exposed to Solidity contracts. In the upcoming Sapphire 0.6 release, the cost of these precompiles has been drastically reduced. So it only costs a few thousand gas to generate, sign, or verify a signature. So let's create an example contract which first generates the key pair, then constructs a transaction. It then signs the transaction and gives it back to the user, who submits that signed transaction back to the blockchain to be executed. So let's start with a new contract. Let's call it example signer.sol, and zero. We're going to import the Ethereum utils class in here that we discussed. Example signer. You can make the constructor. You're going to make the constructor payable so that any gas you pass when deploying the contract will be passed back to the address of the key pair that it generates. And for the key pair it generates, we need to define two variables. We need the address, that's public, and let's call this a gas paying address. And then create the secret, which is private, obviously. Let's call this gas paying secret. Now in the constructor, we do a gas paying address and gas paying secret equals Ethereum utils dot generate key pair. And now when you deploy this, it will generate the public address of the wallet, and it will keep the secret for the wallet private, so nobody will be able to access it. Next, we need to create two functions. So one function will generate the transaction, and the other function will be called by the transaction. So if we say function create transaction, and this is a public view call, so it doesn't require any gas. And then we get another function, so function called by ourselves, which is a public function, and we're going to say that it can only be called by us by the gas paying address. So message.sender equals gas paying address. Let's create an event just to see this works. Event test event event example, and we're going to emit the test event with just a random parameter in there. So in the create transaction, we now have to import the EIP155 signer class, and then we'll be able to construct the transaction. So if we say in here, we're going to use a EIP155 signer.ethertx memory transaction equals, and then in the parameters for the transaction, we're going to have to fill out everything that's required. So nonce, we need to provide a nonce value, gas price, we need to provide that as well. For the gas limit, let's say 1 million gas. We're sending the transaction to our contract. We're not sending anything of value to it either. And the data, I'm just going to fill this as a blank for now, and the chain ID, whichever chain ID we're currently executing on. So with the nonce and the gas price parameters, the contract doesn't have an understanding of what its own account sequence is or what the realistic gas price is. So it has to trust that the person invoking the contract can provide those for it. So let's add uint64 nonce and uint206 gas price. So next we need to fill out the call data for the transaction. Luckily, Solidity has some useful functions for this. So we want to call by ourselves. Let's add an extra parameter here. Example. And in the data, we can do ABI.encode call, and we can pass it the function pointer, which is this.called by ourselves, which will type check the parameters. So we're going to pass the gas price parameter to the example parameter. And you can see it's verified the type of the parameters when it's encoding the call. So let's add example to 1, 2, 3, 4. And then now that we have the transaction created, we can sign it. So we're going to have to return some bytes memory, and we use EIP155 signer.sign. We use the gas paying address, gas paying secret, and our transaction. So if we run through the contract, there is a method named called by ourselves, which can only be called by the address the contract generated. The user calls the create transaction function in a view call, so it doesn't cost any gas, which then generates a transaction using the ABI encoding of the function call to the called by ourselves function, and it returns that to the user. The user then submits it back to the blockchain, which means the contract is effectively executing its own method. We could also create another example consisting of two contracts, one contract on Sapphire and one contract on another EVM compatible chain, where the create transaction function would take the chain ID of the remote chain that could be passed in by the user. But instead of using its own address, it specifies the address of the other contract. Then the other function can optionally be restricted to only being called by the address the Sapphire contract generated. Remember, the wallet the contract generates will need to be funded with gas tokens, and you will need to make sure that the gas price and account nonce values cannot be used maliciously. So let's modify our example to be able to sign transactions for a different contract on another chain. So the first thing we're going to have to do is modify the chain ID parameter. And instead of specifying our own chain ID, allow people to pass in a different chain ID. So next, we're going to have to take in the remote contract address. So if we say, when we construct the class, we have an address of remote contract. We have a public variable, which is the remote contract, and we assign that. And then instead of the current address of this contract, we're specifying a remote contract as the destination address of the call. And we're going to remove this function because it doesn't exist in our class anymore. And we're going to create an interface here. Remote contract, example, test, make that external. And for the encode call, we can use the remote contract interface dot example, and that will encode the call for whatever interface is there, with type checking still taken account for. A great place to start is the documentation. It provides an overview of how to implement and deploy contracts using OPL. Go to docs.oasis.io and click on the Oasis Privacy Layer button. The OPL documentation also includes a full tutorial on a DAO voting dApp, which demonstrates how to adapt an application to be split across chains using the privacy-preserving features of Sapphire for collecting and tallying votes, with the main interface for the dApp on a transparent chain. Source code can be found on the Oasis Protocol Playground GitHub repository.